Hello everyone, so welcome to the second lecture of week 6. So we have started discussion about the pre-training architecture and paradigm, and this lecture I'll discuss about how do you pre-train transformer encoder. So these are the things that we will cover in this lecture. So how do you pre-train BERT, right, that for the transformer encoder, and using a mask language modeling objective. And we will discuss about a very important aspect, and how do you get contextual representations from BERT model. And we will also see the pre-training fine-tuning paradigm, that once you are pre-trained, how do you fine-tune it for various different paradigms and applications. So this we had discussed in the last lecture, that when we are saying pre-training transformers, so we can do any of the three architectures. So we can talk about pre-training encoders. So what will happen? I get bidirectional context, right, and you can condition even on the future tokens. But how do you build strong representations for this? Encoder decoder, you can actually make use of both encoder and decoder, right, and ideally this should be giving a very good representation because you are pre-training both encoder decoder together. But what is the best way you can pre-train them, right? Because see, the central idea of pre-training is that you need lots and lots of data, and you should not require any human label, because once you require human labels, you are imposing limitations on the kind of data that you can use, right? So you should be able to use everything available on the web, of course with some filtering and all. And that's what you can do with decoders, right? You can just do the next word prediction, right? But how exactly you will use this data to pre-train, say, encoder decoder, right? That's what we will see. So what about the encoders, right? So we are saying we can get bidirectional context. So because you are just doing the encoder, you can, each word can attend to everything else, the default way we saw in transformer encoder. So each word can attend to everything else. So you have bidirectional context. But how do we train them, right? So first of all, what exactly do we want to achieve through this encoder model? So I'll feed a sequence of words, tokens, x1 to xn at input, and I want to be able to get a very good representation. So I want to be able to get a representation h1, h2 up to hn. That's what I was typically doing from encoders, right? Encoders give me representation, and decoders help me generate words auto-recursively, right? So I want to get good representation at the final layer of the encoder, right? So I want to map this input embeddings to a sequence of output embeddings, and you see this n and this n are the same. So you have the same number of contextual embeddings as the number of words. And these vectors that you are getting are contextualized using information from the entire input sequence, right? So this is how a causal self-attention layer looks like, that we saw in that we will see more in decoder. So where you're not able to attend to the future tokens, but in encoder I can attend, each token can attend to all the tokens, right? Because you want to make a good representation. That's the only requirement here. So you should be able to make use of whatever information you have to get a good representation for each word. Okay. So how do we achieve this? How do we pre-train an encoder kind of model? And the solution is that, okay, I can't predict the next word, right? That would not be a good way of training them, because I want to make use of the next word, right, to be able to have bidirectional representation. If I'm predicting the next word, just the next word, I can't make use of the future context. So the solution was that, okay, we use something different, and this was called a mask token, right? So what you will do, so suppose you have in the data you have just sentences or so a text. So I went to the store is the sentence that you have, and what you will do, you will simply replace some tokens like went and store with mask, a special token called mask, right? And this is what is the input, right? So now think about this as the input to a transformer encoder, right? What will happen? It will anyway do the self-attention, feed forward and everything. up to all the encoders and build some representations. So it will build representation based on the input I mask to the mask, right? It does not know that this word is went and store. And what is the task you are asking it to do? At this representation, I am asking it to predict the word that should have been the input, right? So this is just a different way of saying what is the next word. You are saying, okay, what should have been the input at this position? So you predict went, right? So you predict went, but how will it do it when it didn't even know the word? Like how a language model does it. It predicts next word. Similarly, it knows what happened before, what happened after. Right? Given that entire context, can you not predict what should have been the word at this point? Right? That is the idea. That so this is a deviation from language modeling objective of next word prediction. So where you mask a token and predict it. An idea is that if you are able to make good contextual representation, like this representation should get information from all the tokens in the sequence. So I should have a very good representation so that I can predict what is the word that I had masked. Right? So you can so typically what you should do, you add loss only for predicting the masked word, because otherwise it may be too easy to predict the word itself, right? I, to, and the. So whenever I have masked, I'll predict the word, right? And this so you are predicting x given x tilde, the masked version, and this is why it is called a masked language model, right? Now the authors use certain more tricks to ensure that you get good representation, right? Because how would you finally use it? You will use it when you are given a sentence like which will not have mask, and you should be able to get good representation. But the way we are seeing it here, because we are computing loss only when the token is masked, it will learn that okay, I will have to make representation whenever I am masked. Otherwise, I don't care about this representation because nobody is computing a loss from that, right? So what the authors did, they said, okay, so let's not make it completely predictable. So what we will do, so we will not let the model get very complacent. So what I will do, I'll make good representation even for non-masked words. So how? See, the transformer will not know at which point, at which token you will create the loss, right? So what you can do, so you will anyway create the loss whenever it is masked. But even otherwise, you can randomly take some tokens and create loss. Like this word too, you didn't mask, but still you can create a loss that you predict what was the input word, so that it is not complacent. It still has to make a good representation so that it predicts this word. Or some words, instead of masking, you replace them by a random token. Now this does not know that you have replaced it with a random token, right? But it has to still predict that the word should have been went. So you are trying to trick it at multiple ways so that it makes a good representation irrespective of whether this was the same word, this was a replaced word, this was a masked token. You will not know at which token you will be quizzed, right? You will be quizzed and asked to make a guess of what is the input word. Right? So this typically they did. They said, okay, 15% of times I will mask. Out of 15%, 18% I will actually mask. I mean, 15% of the time I will predict. Right? Among these, 80% of the time, that means 12% of the overall, I will mask the token. 10% of 15%, I'll replace this with a random word, and 10% of the 15%, I'll just keep it as it is, right? So that, yeah, I mean, it knows that anything can be done. I should get good representation every time, right? Because at fine tuning time, there will be no masks, right? You have to make representation for every token. So this is another way I can see the BERT model. So suppose you have this sentence, so long and thanks for all the fish. So you are feeding the word embedding plus position embedding. That's how you feed input to the transformer. And what you do, you mask. So you are masking it with and replacing it with the mask token. Thanks also you are replacing with mask token, and this you are just replacing with a random replacement, right? And you are making a loss at these 3 points. Now this transformer does not know at what point you will put the loss, right? You will put this loss. So it has to make a representation at all the words in the input, so that wherever you put this feed forward plus softmax layer, you should be able to predict what was the original input at this word. So this is how you train the BERT model. You use huge data, mask some words, and other words you don't replace with random words, and predict what should have been the input token. And the architecture is very simple. So you have the whole transformer model here, but once you get these representations, right? So you multiply. So you have these representation H1, H2, Hi. You multiply with this matrix WV that will project it to the entire vocabulary, and so WB will be vocabulary times DH. So DH is the dimension of each hidden layer. So BERT case it was 768 dimension. So 768 times your entire vocabulary is what you would have this matrix, and you get distribution and you apply softmax over that, right? So that you can compute loss with the minus log probability of the ground truth word. So this is your pre-training. So of course they added one more loss with this. So they said, okay, you can do mask token prediction, but you can also do another loss, that is next sentence prediction. And why did that we will see shortly. But what is the idea? So you will give two sentences, S1 and S2. So you'll feed one after another to the BERT model, and they will predict if S2 is a continuation of S1. Are they really adjacent in the data, or are they not adjacent? I mean, S2 is just random sentence compared to S1. So they will simply say if S2 is the next sentence of S1, and but then how would you feed S1, S2? How would you know that that's where S1 ends and that's where S2 starts? So they used two special tokens that became very popular. One is CLS. So they'll feed CLS token before everything. Then they'll feed the first sentence, and they'll feed a separator token. Right? Just like mask, you have two more tokens, CLS and separator. Right? So they are placing separator between S1 and S2, and CLS before everything. And then you have two special embeddings. So you have embeddings for first segment and second segment, and they are added to the input. So you already had the input word embedding, you had the position embedding, you also had the segment embedding, right, for each segment. And right, I mean, then you can think of this as an entire sequence, right, with CLS and separator as extra tokens. And like you are doing in transformer, you will get the embeddings. Finally, contextual embeddings, H CLS, H separator, H S11, H S21. You'll get the hidden or the contextual representation for each word, right? And then what is your task? You want to predict if it is a continuation or not. So they use this CLS token as a special thing to do prediction, right? So they will do classification based on that. Now they could do it at the first word because in encoders you have the bidirectional context. So this token will anyway attend to everything that you are seeing in the sequence. So this will have information about everything else. Remember when we were doing RNNs, we use the last token, right? Because we are going from left to right. So only at the last token you have seen everything, right? Not at the first token. But here, this first token CLS would have seen everything because you are doing bidirectional context, right? So you can use HCLS as some sort of sentence representation. I mean representation for the entire thing, and now you can just convert it to whatever classification way you want to do. So this will be like a 768 dimension, and my classification is binary classification, so I can convert it to say 2-dimension vector, right? So and then I'll predict if it is a continuation or not, right? I'll do softmax, I'll get two probabilities. Is it a continuation or not, 0 or 1, right? So that is what can be done for NSP pre-training. So something like that. So you have cancel my flight and the hotel, you have put separator, you have also segment embeddings, right? So XS1 and S2 segment embeddings, and you're feeding it through this transformer encoder, and only from the CLS you are applying this WNSP, that is 2 times TH, because you have two classes times TH, that is 760 dimension, and you are doing softmax to predict, and to compute your loss, right? If it really predicted the continuation correctly or not. Now, why did they add this next sentence prediction loss to the MLM loss? Now, the reasoning was that many of the tasks required more than one sentence and doing certain reasoning between them, right? So, and they wanted to do the task using BERT. So, for example, if you're simply masking words, So you get good word level representation. But there are many applications that require relation between sentences, like paraphrase detection. Is this sentence, are these two sentences have similar meanings? Are they paraphrases of each other? Entailment detection. If the two meanings entail each other or contradict each other, or they are neutral to each other. Discourse coherence, right? So if two neighboring sentences form a coherent discourse. So you have multiple tasks where you are reasoning by taking two sentences as input or two pieces of text as input and trying out if they are similar and different things. And they said if we do this next sentence prediction pre-training task, maybe it will learn to perform tasks that require that require reasoning among multiple sentences. Okay. So finally, after pre-training, they had two models that they had released. So BERT base and BERT large. So BERT base had 12 layers, 760 dimension hidden states, 12 attention heads, and 110 million parameters. So this was the most popular model, right? After this came, and there was BERT large that had like 24 layers, 1024 dimension hidden states, 16 attention heads, and 340 billion parameters. Now it may be a good exercise for you to try out and see if you can get this 110 million parameters. The hint is that you use the same formula. So we have just the encoder, transformer encoder, and we have the 12 layers, 12 attention heads, 768 is the model dimension, and feed forward will be 768 into 4, the feed forward hidden layer. Plus you also include the vocabulary parameters, because the vocabulary was close to 31K and you need 760 dimension embedding for each word in the vocabulary. So you include that and you will see if you are getting close to 110 million parameters. Now this was trained on book corpus. So that time the corpus was not too big, right? That's what people do now. So this was just the 3 billion token corpus, and they used 64 TPU chips and for a total of 4 days to pre-train this. But that was also too much at that point of time. But the interesting thing was that, okay, we needed a lot of compute, but you pre-train only once, right? And then once you pre-train, you have fine-tuned it like thousands of times since then. So you fine-tune so many times. So pre-training is done, you save the weights, right? So you save your checkpoints, and then you start from there and fine-tune for different applications, right? So this was the model BERT. Now, as we are saying, so one important thing that we do with the encoder models is to learn contextual representation, right? So you have feeding this token. So the CLS you will typically always prepend to the sequence, and you have so long and thanks for all the. What you get is the embedding, contextual embedding of each word in the input at the last layer. So if you want what is the contextual representation for thanks, you say, okay, I'll just take HL4, and that will be my contextual representation. Now, why is this contextual representation important? So we have talked about this briefly, like given a word, I can get word embeddings. So this is what is called a static embedding. So we have seen word2vec glove, where people have just created dumps of word embeddings, right? So you have you can just get this, download this dump, and you can get, okay, given the word say die, I know the embedding for the word die, right? So this is a static embedding, this will not change. But what do you mean by contextual embedding is that depending on the context, you want a representation for the word. Like the word die can be a German word. Even in English, you may have single person dies, multiple people die, a playing die, right? I mean, this and this would have very different context. They should not have a similar representation. So, but they would have similar representation if you are using a static word embedding. You can only represent one, or you can represent an average of multiple senses, right? But if I want to represent different senses separately, I should be able to give different representation based on the context. And that's what pre-trained models can do, because they have, pre-trained a lot of parameters already by huge data. Now you give a sentence, I can pass it through this pre-trained model and get the representation for die, and this will be different for the two contexts, right? Depending on the context, this will be entirely different. And ideally, these two will get similar representation. This will be similar, but this will be very different from the representation for a playing die, right? So that is the idea of contextual word representation, and these all should be very different from the German die. Now, how do you get contextual representation from BERT? Is not so difficult. So, you pass the sequence of words prepended by CLS, and you get the H help, H prints. You get the embedding for each word, right? So, you have this 12 layers of BERT, and you can get first layer, second layer, third layer. You can keep on getting the representations, right, at every layer. So, now the question can be like, which of these representation will I use? So, default answer can be, okay, I'll use the final 12th layer representation as the contextual representation for each word. But I mean, there were a lot of experiments that were done to see what typically works best. So, this was one paper where they found what is the best contextual embedding for any word in a context, and they tried it for NER task Connell data set. So, what they said, okay, if I just use the first layer contextual representation and then just use that representation for doing a task. So, they found this was like 91, gave you a score of 91. If I use the last layer hidden layer, immediately you have a huge boost, like 94.9. It's a much better contextual representation. What if I add all the 12 layers, right? So, that can be one other way. I have, just like I was doing in Elmo, I was taking multiple layers and doing task is specific, but I can just do average, and this gave further boost. Then they found, okay, if I use 11th layer, that even better. This was strange, but if I take the last 4 layers sum, that was like very good among this. And instead of adding, if you just concatenate last 4 layers, you get even better. And this became some sort of like default understanding in the community, that if you just want to use this for contextual embeddings, you can take the last 4 layers 9, 10, 11, 12, and you can take their embeddings and concatenate, and that is giving you a good contextual representation for the word. Now, coming to how do we use BERT for various tasks. So, we can fine tune BERT. So let us say I have pre-trained BERT. So, that means all the parameters, the 110 million parameters are already trained, and I know these parameters, right. And now I want to really do some tasks, like I want to do sentence pair classification, right. So, I was talking about NSP. So, you have 2 sentences, you want to classify, say if they are entailing each other, contradicting each other, neutral to each other. You may have a single sentence you want to classify, like you may doing sentiment analysis, you are doing spam detection. So, you want to classify into spam, not spam, positive, negative, neutral. So, you want to do multiple tasks, or you want to do, say, NER tasks. So, you are given a sentence, you want to find what are the named entity tags from that, or any new task like squared question answering was a new task where you have a question and a paragraph, and you want to find out what is the answer to the question within the paragraph, right. So, you have a span in the paragraph that answers the question. So, any span based task. So, we will see how you can use this BERT pre-trained model. You can fine tune it for various tasks, and the essential idea is just transfer learning, right. So, that is the power of these models lies in their ability in extracting the generalization from large amount of text on which they are pre-trained, and because they are pre-trained on huge data. So, I want to just make use of this generalization, and how do we do that? We create some sort of interfaces from these models for various downstream applications. So, I have this pre-trained model. Now, tell me how do I use it for classification or NER and so on, right. So, we will create just some interfaces, and these interfaces are called a fine tuning process, right. So, what fine tuning will do? So, on top of this pre-trained model, I will create one application, that I will create a classification application, I will create the sentence pair classification application, NER, right, and so on. And the way I do it, I add some small set of application specific parameters, right, and I have to find out what are the best value for these parameters, right. But that is all. I mean, these are very, very small compared to 110 million parameters that I have pre-trained for BERT, right. So, that means I have some parameters to train. So, I need some data. So, I need some label data from the application to train these additional parameters. And what about the 110 million parameters? Do I touch them? So, there are, I mean, different ways. People have either tried freezing them entirely, or you can only make some minimal adjustments. So, you really focus on training your application specific parameters, but this 110 parameters, your learning rate may be very small, or even like a decaying learning rate where you change your upper layer more, because upper layer are more task specific than the lower layer that are more general representation level, right? So people have tried different adjustments while fine tuning. So so like, let's say, how do you do sequence classification? So how we are doing sequence classification RNN? So I used to give a sequence x1 to xn. I get a representation h1 hn, and I use the last representation, right, to stand for the entire sequence. I said this is the sentence encoding, right? Now again I'll come back to the same task. Like in the case of BERT, what is my sentence encoding? Now we anyway have a special token CLS, right? So we are depending the sequence of the CLS, and this HCLS is the sentence representation. So I simply use this HCLS as the sentence representation, and on top of that I do exactly whatever I was doing with RNN and LSTM. So I create some simple linear model to do classification, right? So you add this, you have added this CLS token to the vocabulary, and you prepend it to all the input sequences before they start, both during pre-training and encoding at inference time. And the output layer vector in the final layer of CLS, this will serve as the input to the classifier head. So what you will do, so let's say we have RDH, so DH dimension vector in the final layer, so CLS is DH dimension, and I have k classes in my output. So I will simply use DH times k parameters in my linear layer to project my final representation, sentence representation to the classes, right? And then I will do softmax, and this will give me the probability over classes. So I only have k times DH parameters, and this will be very small. You see, DH is around 768, and k is the number of classes. Let's say 5 classes. So some 3000 parameters, right? 3.34 k parameters. Very small compared to 110 million parameters. Right? Sorry, this is 3.84 k parameters. So yeah, I mean that's what I do. So I pass this entire sequence. I have this pre-trained model already. I create this interface. I say, okay, HCLS. Now you have this additional matrix that will take this HCLS embedding to number of classes. This is sentiment classes classification. I may have 3 classes. So I have this additional parameters, and you give me more data. So you will give me some data, say 500 data points, 1000 data points. So I'll train my model. So I'll feed the data. I'll compute the output. I compute the loss, back propagate, update these parameters, and I can decide whether I want to freeze these or change them very slightly. So I can either freeze these or change slightly. Right? So this is what I can do, and that's all is there to fine tuning, right? So adding this additional application specific parameters and using some additional data to tune these and fine tune these, right? So that's how you do sentence classification. Similarly, you can do sequence classification. So pairwise sequence classification, where you have a pair of sentences, and let's say you are doing entailment, contradiction, and neutral. So, and they will describe what is the relation between the meaning of the first sentence, the premise, and the second sentence, hypothesis. So like, John walked back to the town to the smithy. John traveled back to his hometown. So this do not neither contradict nor entail. So the label is neutral. Tourist information offices can be very helpful. Tourist information offices are never of any help. So this is clearly a contradiction. I am confused. Not all of this is very clear to me. This is entailment, right? So you will be given a pair of sentence S1, S2, and you predict this label. Right? That is the task. How will you do it using BERT? So you know I will do, CLS. I'll pass S1. I'll do separator. I'll do S2, and I'll get the embeddings for all. So say HCLS is what I will use for this classification. Right? It's very similar to the normal classification. So I pass sentence 1, separator sentence 2, and the CLS token gets the embedding, and that's where I do the prediction. Right? So very similar to sequence classification. Just what changes is the way you are formatting the input. What about sequence labeling? Suppose you are doing NER, right, named entity recognition, where you have to predict, say, BIO tagging scheme. So same thing, you will pass the CLS token and all the tokens in your input, get the embeddings, contextual embeddings, and then rather than predicting at the CLS where you will not do anything now, each token you have a predictor, right, like you were doing in the LSTM. So at each representation H1 you have 768 dimension representation. Fine, you will pass through a linear layer that will take it to the number of labels in your tag set, right. So like if you're doing NER, it will be 2 times number of tags plus 1 for BIO tagging scheme, right. So how many weights do you need additionally? It's simply your DH times k. This is your tag set 2k plus 1, right. That many weights do you additionally need. Everything else is exactly the same. So you see how it makes very easy once you are using this pre-trained model to make use of this in various applications, right. So you see a connection between how we are using it for classification, sentence pair, and NER. Like pause tagging is very similar. Similarly, you'll pass CLS entire sequence, you get the representation, and you know the number of tags that you are having in your tag set. So you will simply predict among one of the tags, right. So you to take some training data to tune these parameters, fine tune these parameters, and you're ready with a pause tagger based on BERT model. Okay. So there is one detail that I just wanted to discuss regarding NER and BIO scheme. So we talked about BIO scheme, right. So suppose this is the sentence, Mount Sanitas is in Sunshine Canyon, and these are the named entities. So in BIO scheme, what I will do, I'll call Mount as beginning of location, Sanitas as intermediate of location, is as O, in as O, Sunshine as beginning of location, and Canyon as an intermediate of location, and finally I have this dot as outside, right. This is standard we saw. But now this becomes a bit problematic with subword tokens, right, because now we are using BPE. So it may happen that these are my subwords. So after word piece tokenization, like for example, I may have empty and dot as 2 different tokens, Sanitas, San, and Itas as 2 different tokens, and yeah. So you see, so this is not the same sequence as here, right. So what will I do? So I have to decide what do I do at the training time and the decoding time. And the way people do it, I mean one standard way is, so you repeat the tag at training time. So you will set 2 beginning location, although beginning location should be only 1. You just copy this beginning location at both the stages, right. So the gold standard tag that is there with the word, you copy it to all the subword tokens, right. That is what is done. So that's how you train the model. So you will predict 2 beginning locations. At the inference time, at the decoding time, what you will do? So decoding time, you will anyway just decode something, right. So you have decoded a sequence. How do you convert it back to a sequence that you will map? So suppose empty had got something and dot had got something else, but you want to make a single prediction for empty dot. So how do you reconcile? So the way it is done is that, okay, so you say, okay, I'll just care about the first subword token of a word. So I'll see what is the token, the tag that is given to empty, right, and that is what I'll copy to empty dot. So this is another trick that is used, right. Of course, you can do better. I mean, you can combine these, but this is one trick that is commonly used. So I have some prediction for empty. Let's say beginning of location, and dot get I of location. So I want to predict what is the tag for empty dot, right. That's what my task is. So I simply copy this tag to empty dot. I'll say this is beginning of location. So that is one detail, right. So we have still not talked about how to use BERT for fine tuning other span based application like question answering, reading comprehension. So this we will see in the next lecture. So you can read more about it in the chapter 11 of our book. So thank you.